Good morning. So my talk is centered about lateral movement, which is one of the important stages in an APT, in an attack life cycle, but not really in the conventional ID sense. Instead, I want to talk about lateral movement in the context of network slicing, which is a very interesting feature introduced in the 5G networks. So before we delve into the talk itself, a little bit about us. So my name is Ayush, and I'm a cybersecurity scientist at ST Engineering, where I've been working on multiple R&D projects in IoT, industrial IoT, and 5G security. I've also been involved in teaching local polytechnic students and also collaborate with our InfoSec business side. And this work was done with Dr. Ting, who was not able to make it here due to her busy schedule. She's the Senior Vice President and Head of Cybersecurity Strategic Technology Center at ST Engineering, where she provides thought leadership and oversees cybersecurity technology innovation. All right. I thought maybe let's start with a quick primer on 5G technology itself. So for those who are unfamiliar, 5G is the most recent standard for mobile communication, and it provides major enhancements compared to earlier cellular technologies. With 5G, high data transfer rates up to 10 gigabytes per second, very low latency, below 1 millisecond, high-speed mobility up to 500 kilometers per hour, and high connection densities, 1 million per square kilometers are possible. The applications of 5G can be, they mainly come under three categories. One is, as you can see, enhanced mobile broadband, or EMBB, which improves upon the existing mobile broadband services by focusing on higher data transmission speeds. The second one that we have is the ultra reliable and low latency communications, or URLLC, which basically appeals to industries like healthcare, manufacturing, which need highly reliable data transmission. And the third one is massive machine type communication, or MMTC, which supports a high density of devices in a particular region with low power consumption. So this is how a 5G network architecture looks like at a higher level. It consists of, for one, the radio access network over here, which includes UEs, or user equipments, which basically mean your smartphones, tablets. And then it has several base stations, each of which cover a particular geographical area. And secondly, we have a mobile core, which is a collection of various functions which provide several services, such as device authentication, device tracking, and so on. So the mobile core architecture looks like this, and it adopts a microservice-like architecture with a set of functional blocks, each of which is called a network function, or an NF. And these NFs are divided into three groups, two of which run in the control plane, which is shown as dashed lines, and the rest, the last group runs in the user plane. So what is network slicing? 5G networks implement this feature called network slicing, which is basically a slice is isolated end-to-end network, which is tailored to meet the diverse requirements of a specific application. Some use applications for network slicing are voice communication, video streaming, and e-health. And network slicing basically allows 5G networks to support a wide range of services with varying service level requirements. And it also allows for the creation of multiple virtualized and independent logical networks on the same physical network infrastructure. NFs in a 5G core are typically deployed as containers, whereas network slices can be implemented as VLANs, wherein each VLAN can consist of a set of NF containers. This is how network slicing implementation in a 5G core looks like. So you can see there are certain there's a set of common NFs which are shared amongst these slices. And slice 1 here consists of instances of SMF, UPF, NRF, PCF, and then another set of instances for slice 2. So these are all network functions. Now, it's not that 5G networks have not been designed keeping security in mind. In fact, the 3GPP standards for 5G networks have mandated several security features for 5G networks. The main standards document covering security architecture and procedures is this 3GPP Technical Specification 33.501. It covers topics such as overview of security architecture, security procedures between UE and NFs, security for non-3GPP access to 5G core, service-based interfaces, non-service-based interfaces. And then I've highlighted a couple of topics that it covered in the context, covers in the context of network slices. So one of which is management security for network slices, and the second one is security procedures for network slices. Now, management security for network slices covers secure access to slice management interfaces and secure access to slices by UEs under release 15 of the standards document. And under release 16, it covers primary authentication between UE and 5G core and secondary authentication between the 5G core and the data network. However, just having security standards in place doesn't protect 5G networks. Issues during implementation of a 5G core product by a vendor can introduce vulnerabilities. Sometimes the 3GPP standard specifications themselves are vulnerable to exploitation. Several such vulnerabilities have been discovered by academic as well as industry researchers. What is also noteworthy is that the current 3GPP standards don't make any recommendations covering the security of NF container images, NF container runtime security, or NF container host and inter-NF communication hardening. Existing proprietary as well as open source 5G core products are known to have several security vulnerabilities and are therefore prone to compromise. In fact, cyber attacks on 5G networks have already begun, as evidenced by the attack on Vodafone Portugal by LAPSUS hacking group, which was reported in Feb 2022, and the targeting of Maxis Communications, closer home in Malaysia, by the Root K1Kit hacking group, which was reported in Feb 2024, which is this year itself. So cyber attacks targeting critical and complex infrastructure, such as 5G networks, usually consist of multiple stages, with lateral movement being one of them. And here is the typical cyber attack life cycle with lateral movement stage. So our focus in this talk would be on malicious lateral movement strategies in a 5G core with network slicing. The main idea behind this type of lateral movement is for an attacker with a foothold in the 5G core to pivot to a connected network slice or move across slices. This can enable attackers to, for one, reach NFs which are not directly connected to the NFs to which they have initial access, and two, establish foothold in critical network slices such as e-health, autonomous mobility, industrial IoT, which they may not have access to initially. And as I mentioned before, NFs in a 5G core are typically deployed as containers. And enterprise containers have already been targeted by attackers in the past. For example, the cloud management firm Upticks and the cybersecurity, well-known cybersecurity firm CrowdStrike have reported attacks on their honeypots, which were basically Docker servers. They were used to install malicious container images for crypto mining. Microsoft Defender for Cloud team has also reported about Kinsing malware, which was compromising Kubernetes clusters by exploiting RCE vulnerabilities. So we have proposed two types of lateral movement that an attacker can mount in a network slicing environment, which have not been proposed before. The first one is a same slice lateral movement, and the other one is cross slice lateral movement. So let me show you how that works using one of the earlier figures. So basically, in a same slice lateral movement, what you try to do is you try to pivot between the network functions in the same slice. So you can move from SMF to NRF or NRF to UPF. Whereas in cross-slice lateral movement, what the attacker tries to do is it tries to pivot from a network function in one slice to another network function existing in a separate slice. For example, from SMF in slice 1 to maybe UPF in slice 2. Some of the attack techniques which can be used for achieving this kind of lateral movement are container escape, which can be used to pivot from an NF container to the underlying host. Attackers can also use container misconfiguration to pivot from a compromised host to NF containers deployed on a target host. And they can also exploit open ports for remote access to pivot from one NF container to another remotely. To demonstrate how such network slice lateral movement could work, we built a 5G test environment using open air interface software, which includes Docker containers corresponding to various 5G core network functions, as well as the OAI GNB, which is the base station, and the 5G NR or new radio UE emulators. These container images were deployed on a VMware ESXi server VMs. Also to be noted is that the OAI 5G core network implementation is very much compliant with the 3GPP standards, specifically TS 23.501. And all the features of the core network components are continuously tested with professional testers, and commercial GNODBs are tested with commercial off-the-shelf UE, as well as open source radio access network simulators. So this shows you the architecture of the 5G test environment that we built. And it consists of 6 slices, some of which share network functions. So let me show you a small example of how single slice lateral movement might work using our 5G test environment. So here's a small video showing that. So basically we are in the container shell for one of the network function containers in a slice. And then what the attacker tries to do is it tries to list the running processes and looks for those processes running under root and uses GDB to try to debug that process. Next, it makes a system call to try to obtain a reverse shell back to the attacker's machine. So by doing this, the attacker would be able to escape this NF container and basically obtain access to the underlying host. And once it gains access to the underlying host, it can access other NF containers which are deployed on the same host. Sorry, I think it's better to, yeah. So once it makes the system call, then there's a listener process at port number 444 in another window on the attacker's machine, and it obtains a reverse shell. So it seems like, yeah, went out of display. Sorry for that. You'll have to bear with me because we're having difficulty seeking various timestamps in this video in the display view. But this one should go quick enough. So GDB into the process and then make the system call. To obtain a reverse shell back to the attacker's machine. So this is the IP address for the attacker's machine, and there's basically a process listening at port number 444. So we haven't made the system call yet, and now we'll make that call. So we have obtained a reverse shell. And since we have escaped the container and to the underlying host, now we can have a look at all the running Docker containers, including the NF containers on that host. So this is all happening within the same slice. And now we can actually obtain shell access to one of the running NF containers. Yeah. So let's move on to the next slide. This one shows cross-slice lateral movement, how that might work using the same test environment. So let me pause this. So we have to view this in conjugation with the previous video. So basically what we have done is we had access to one of the NF containers. We escaped to the underlying host, right, in the same slice. And once we have obtained access to the underlying host, from there we will try to access one of the other slices, which goes like this. So as you can see, these were the NF containers we also saw before, running on this same 10.23 host. And now we'll try to access the NF containers running on another host in another slice. In fact, it has multiple slices running on that host. So this is another host 10.7, which has the Docker port 2375 open. So it's easy to access remotely all the Docker containers which are running on it. So we just select the SMF container running in slice 2 and obtain a shell access. Yeah. All right. So this basically shows you that both single slice and cross-slice lateral movement are indeed feasible. Next, what I wanted to show you was an APD style attack campaign in a 5G core, what that might look like. So this is the last demo from me today. And we assume that the adversaries belong to an APD group which wants to target a critical 5G network slice, for example, a government e-health network, to access confidential data or to disrupt the provision of health services to legit customers. And specifically, the adversaries aim to drop the health services customers' data traffic by gaining control of the UPF, which is the user plane function in the e-health network slice. So this is the last demo. Just bear with me for this. So first, what the attacker can do is it can try to use Shodan to try to see which Docker containers have publicly exposed ports or APIs over the internet. So you can actually do that. If you have a Shodan account, you can actually go back home and try this. And then if you have a paid account, then you can actually show you the IP addresses of the Docker servers which have these publicly exposed ports. Unfortunately, I don't have that. So, and also since this is a simulation, so I'll be using my own server to demonstrate the attack campaign. So suppose using Shodan search, the attacker got hold of this IP address 10.23, which has an open Docker service port 2375. And then it uses that to list down all the NF containers which are running on that host. So it selects one of the NF containers, which is AUSF, or authentication server function, and remotely tries to obtain a bash shell on that container. Then it's trying to open a listening process at port number 5555, and then another one at port number 4444. So next, what it will try to do is to maintain persistence, it will try to obtain a reverse shell back to the listening process using the listening process at port number 5555. You can think of it as a compromised device trying to connect with a command and control server and maintaining a connection for persistence. So right now what you just saw is it copied a malware sample using the same open Docker service port to this AUSF container. And using this malware sample, it will run this malware sample and then obtain a reverse shell back to the attacker's machine. Yeah, so it's running the malware sample now, and by now it should have obtained a reverse shell back on the attacker's machine. Yes. Now the attacker is trying to open another bash shell on the AUSF container. And then we'll use the same container escape technique that I demonstrated to you earlier to escape to the underlying host. So it's looking through all the running processes, trying to see which ones are running under root and which one it might be able to use for container escape. Just bear with me on this. I'll try to move quickly in the next few slides, which I think I have only 4 left. So it's still trying to find a process which it might be able to use with GDB. So here I'm using a process which, it's which was easier for me to use with GDB, but I mean, if you work upon it, there are definitely many other processes which you can use with this technique to accomplish container escape. So again, it makes a system call to obtain a reverse shell from this container to the attack machine, so that it can escape to the underlying host and then access other NF containers, scan through them. So 10.27 is the attacker machine, and we have already been running. I mean, the attacker has already been running this listening process at port 4444. Now we'll go back. Already obtained a reverse shell, so now it will try to figure out what to do next. So since it has obtained a reverse shell, it will try to, and it has escaped to the underlying host. So now it will try to list the other NF containers running on that host, see if it can attack some of them. So it has decided to execute commands on the SMF container. And you don't really even need a shell. I mean, you can just using the exec command, you can just start executing commands on the container without even obtaining a shell. And since it has access to the underlying host, so now it will try to scan the environment. It will try to scan the connected network for other hosts, what kind of services are running on them. Do they have any Docker services or any other services which can be exploited? So yeah, it does find a few hosts, and on some of them it can see that SSH services running. One of them HTTP services running, so it might try to exploit the one with open SSH port. Again, this is just a demonstration. I mean, I have simplified a lot just to show the techniques, but a real attack would be much more complicated. So for example, the attacker might already have access to some SSH keys, stolen SSH keys, which it might try to use to log into that 10.7 host, which is running another slice. So it will now try to copy one of those stolen keys to the AUSF container, which it obtained access to earlier, and then copy it to the underlying host using Docker. So it's copying this key IDs underscore RSA to the AUSF container. So once it copies the keys to the AUSF, it will try to copy the same key back to the underlying host from the AUSF. Okay, so now it has copied the keys to a USF. And the next step is going to be copy the key back to the underlying host. So it's copying the stolen SSH key. Once it's able to copy the SSH key to the underlying host, then it will try to use that stolen key to log into the other host running another set of slices, which was 10.7. Since we already saw that the SSH port was open during the Nmap scan. So now the underlying host 10.23 already has the SSH key. Now it's going to try to log into 10.7 host. Using the key that it just obtained. So it's able to log in to the other host, 10.7, and list all the running NF containers, slices. And then what it can try to do is it can try to access one of the critical NF containers, for example, the UPF, which is user plane function, which carries all the data traffic for the users. And once it's there, it can really do anything. I mean, it can try to drop the user traffic to cause denial of service. And it can be as simple as just changing the routing table. So yeah, it has obtained access to UPF now. So you get the gist. All right. So now that we have seen that APT style campaigns, including lateral movement as a stage, are feasible in a 5G core, which is 3GPP compliant, the question arises, why should 5G network operators bother to prepare 5G core networks for APT campaigns? Though APT campaigns are not common as of now, but they're bound to increase in future with 5G networks becoming more and more widespread, and such networks offer a lot of lucrative targets to well-resourced adversaries. For example, by targeting the UPF, they can access user traffic which can be dropped. By targeting NRF or the network repository function, they can access tokens used to authorize various services provided by NFs to each other. And they can also exploit these tokens later to cause denial of service. By targeting EMF, which is the access and mobility function, they can access the control plane signaling traffic, which can be dropped, leaving the 5G network operator unable to track network access requests by 5G devices or their locations. By targeting critical network slices, they can also hold the customers using those slices to ransom, disrupting their operations. Moreover, given the complex architecture of 5G core and the number of components involved, it's very difficult to secure it completely, leaving gaps which attackers would want to exploit as much as possible. And since 5G core implementations are based on cloud and containerization technologies, attackers can repurpose their existing attack vectors targeting those technologies to infiltrate 5G core networks. And finally, given how critical 5G networks are for commercial end users, enterprises, a successful APT campaign can cause severe financial, reputational, as well as operational damage. So I'll quickly go through certain recommendations or guidelines that we have to prevent NSLM or network sliced lateral movement. For 5G core networks which are not yet deployed, network operators can use strong authentication mechanisms for publicly exposed API access to NFs, for example, using API keys, OAuth. NF container images should be scanned for vulnerabilities and misconfigurations before using them for deployment, and any vulnerabilities found should be immediately patched. Since NF container capabilities could be exploited by attackers for container escape, as we have seen before, NF containers should only have minimal capabilities enabled. And these containers should only expose ports such as for SSH, which might be needed by the operators, and all other ports should be closed. Further, SSH private key should be securely stored. NF containers should be run with minimal privileges, such as non-root user mode, and their access to the host system and other containers should be very limited. The communication between NF container and the underlying host, as well as the communication between the NF containers, should be minimized, as it creates avenues for exploitation. And in addition to these measures, 5G network operators should also follow our recommendations to prevent and detect lateral movement in 5G cores, which are already deployed, which I will cover next. So 5G core deployments, which are already existing, network operators can use, should use security tools for monitoring the activity of NF containers on a continuous basis and respond to alerts caused by any anomalies. And they should also use tools to map the interconnections between the various NF services, their permissions and network communications to provide a clear view of the communication pathways and identify any potential vulnerabilities. Similarly, connections between hosts and those, connection between the host and the connections between NF containers and the underlying host should be mapped. Behavioral analytics should be used to identify anomalous NF containers or service behavior or communication, which might indicate attack. Finally, operators should take periodic snapshots of running NF containers and scan them for vulnerabilities. This can help detect those vulnerabilities which have been missed during the build or deployment phases. So to quickly summarize, cyber attacks on 4G, 5G networks are a real threat. And though there is a comprehensive set of 3GPP standards for 5G system and network security, it's clearly not sufficient when it comes to preventing network slice lateral movement, which is an important stage of a multi-stage attack campaign. We introduced two types of network slice lateral movement strategies, single slice and cross slice, which use underlying techniques such as container escape, container misconfiguration, and exploitation of open ports. Through demonstrations, we also showed you that NSLM and multi-stage APD style attack campaigns are feasible in 3GPP compliant 5G core network test environments. And finally, we gave a set of guidelines for 5G network operators to prevent and detect network slice lateral movement in the 5G core network deployments, whether they're existing already or they are to be deployed in the future. So with this, I've reached the end of my talk, and this is my contact if any of you want, has any further questions outside this session, and I'd be happy to answer them. Thank you.